Now this is a typical type of problem that you run into for limiting reactants. The key thing to realize here is that they've actually given us the amounts of all the reactants involved in the reaction. But first, before we move on, we need to have a balanced equation before we do anything else. Now remember, the language of the equation is in moles. It is not in grams. So the mass that they gave us of the ethane and the oxygen gas needs to be converted to moles before we do anything else. Now, by now, you should be pretty comfortable with this calculation. A lot of people do it as dimensional analysis, but once you get the hang of it, you just realize that when you're going from grams to moles, you're simply just dividing by the molar mass. In the case of ethane, it's approximately 30 grams per mole. So that gives me about 0.667 moles of ethane. And I do the same thing for the oxygen as well. Okay, once we have moles, the big question is, which one is the limiting reactant? There are a lot of approaches to this. Some are very procedural. In other words, you just follow a series of steps. That'll tell you the limiting reactants. That's a little bit dangerous, though, because you don't really understand what you're doing. One alternative way, though, is to actually put things in a table. It's easier to visualize it that way. So that's exactly what I'm going to do. So I'm going to take the moles of C2H6 and the moles of O2 and put them in what we call an ice table. Now, an ice table is a nice way of keeping track of what you start with, what happens during the reaction, and what you're left with at the end. And this is how it works. It's a grid that goes underneath the reaction. And it has 3 rows. And then it also has a column for each reactant, in this case, the C2H6 and the O2, and the 2 products, in this case, the CO2 and the H2O. Now, each row has a letter, I, C, and E. They can be thought of as I for initial, C for change, and E for end. So in the I row, we're going to write down how many moles of everything that we have. Now, we already calculated the C2H6 to have 0.667 moles, and the O2 to have 0.938 moles. Now, initially, before the reaction happens, there is actually no CO2 or H2O because the reaction hasn't started yet. Now, the difficult part is the C. In other words, how do our initial amounts change when the reaction takes place? Now, in order to do this, we need to identify the limiting reactant. And if you look at these 2 reactants, you have to say, okay, which one's going to be used up first? And to look at the balanced equation, it says that for every 2 moles of C2H6, 7 moles of O2 are used up. So that means you need a lot more O2 than C2H6, 3.5 times more. Now we see that we have more O2 than C2H6, but it's not 3.5 times. It doesn't have that 7:2 ratio. It's just a little bit more. So that indicates to us that the O2 is the limiting reactant. However, if it's not as obvious as that, you can use a mathematical method in order to determine this. It's not too hard. You just take the number of moles of the reactant. In this case, I'll look at my C2H6, and I'm going to divide it by its coefficient, which is 2. And I look at the number that gives me. Then I'm going to do the same thing for the O2. Take its number of moles, divided by its coefficient, see what it gives me. What we're looking for is the number that is lower. The lower number tells us the limiting reactant. In this case, the 0.13 is the lower one, so that means that the O2 is our limiting reactant. Now, this is very important because by definition, the limiting reactant is going to be used up in the reaction. In other words, at the end, there's going to be nothing left. So I know I can put a 0 under my O2 as my limiting reactant. Also, what it tells me is I know how much is going to change during the reaction for the C row. So I'm actually going to subtract 0.938 from the initial amount, because basically I'm just doing vertical math. 0.938 minus 0.938 gives me the 0 that I want. What's nice is that this box, the C box, also tells me what I can put in the C box for the C2H6. What I'm going to do is I'm also going to subtract from here as well because I'm still removing C2H6. It's just a different amount, but it's based off of the amount of the limiting reactant, 0.938. And then what I'm going to do is I'm going to put the mole ratio in front of this parentheses. In this case, it's 2/7. And I'm just getting that from the coefficients of the C2H6 and the O2. So this amount is the amount that I'm going to be subtracting from 0.667. So I get 0.268. So I'm going to take my 0.667 minus 0.268, and that will give me what goes in the E box for C2H6. What's nice about this tells me how much C2H6 I have in excess. This is how much is going to be left over. And then I can also use my limiting reactant to predict how much products I'm going to do in a similar way. Now I'm going to do it just like I did for the C2H6, but since we're on the product side, we're going to add instead of subtracting. So for the CO2, I'm going to still use that 0.938, but I'm going to use a different fraction. In this case, I'm going to use 4/7, and that's just coming from the coefficient for CO2 and the coefficient for my living reactant. We're going to make 4/7 the amount of CO2 compared to compared to the O2. And that gives me 0.536 moles. So 0 plus 0.536, again, I'm just doing vertical math, gives me 0.536 moles. Okay. And then finally, I'm going to do the exact same thing for the H2O, even though I don't have to because the problem's not asking for it. It's pretty easy. I'm going to add a fraction of 0.938. In this case, it's going to be 6/7, which gives me 0.804. So my number of moles at the end for H2O is that number. Okay. Now we're not going to do it here, but converting the moles of the various reactants and products is very simple to get back to grams, just multiplied by their respective molar masses. What's nice about doing the problem in the form of an ICE chart or an ICE table is that it lays everything out and it helps you really organize your information. And that's a very, very key skill in doing these more complex multi-step problems. All right, guys, hope this helped. I'll see you later.